Hello, my name is John Deere and I'm going to make a presentation today on some recent research that we've been doing at Imperial College. We have quite a large team of people doing experiments and modelling, and the two lead postdocs in this are Dr. Haibao Liu and Dr. J.Liu. But you can see there's quite a number of us engaged in this research. So we're going to talk today about the effect of impact velocity and impactor shape on the impact performance of composite materials. And of course, when you're dealing with aircraft and commercial aircraft, however careful you are, you cannot avoid the possibility that you may drop a tool on a composite wing surface, or on takeoff you may pick up some runway debris and it could impact against the underside of the wing structure. So these are all possibilities that can occur. So what we set out to do with this research is to look at two effects. First of all, the effect of impact velocity, which in fact many researchers have looked at over the years. But secondly, we want to look at the effect of impactor shape on the impact response and damage in composite laminates. And you can see here the two types of impactor that we employed. We used a conventional round-nosed impactor, and over here on the right we used a flat-fronted impactor. And both of these impactors have a diameter of 16 millimeters, and they have approximately the same mass. So the idea is that we are going to fire these impactors at our composite panels. The composite materials that we are researching are a T700 epoxy prepreg, which is produced by one of our Chinese sponsors of this research. B.R.K are the company that sponsor a lot of the impact research that we do on these composite materials. And we also receive support from BM and also from Battery Comac. So these materials were actually prepared for us by ACC at B.R.K, and if we look at the layup, you can see they have a layup which is plus 45 3 plies, 0 3 plies, minus 45 3 plies, and then 0 3 plies, and it's a symmetric layup, and the specimens are 150 by 100 3 millimeters thick. So we use a standard configuration for testing these, where the composite sample is clamped. These are rubber mounted clamps which pin the sample down onto a frame, and then after the impact event we use a C-scan device, a Sonotest C-scan device, which has a little encoder so it can track the motion of the sensor across the surface, and then it produces a 2D scan of the composite specimen. So the two impact velocities we used were 2.4 and 4.16 meters per second, giving us two different impact energies of 15 joules and 45 joules. You can see here the configuration up here, two different types of impactor, and in each case we tested 3 samples. So this just shows the effect of impact velocity initially. So this is the round-nosed striker impacting against the composite panel, and you can see that we've got two energies. We've got the 15 joules and the 45 joule energies, and the higher energy is the black curve that you can see here. The lower energy is the blue curve. Now, as you might expect, as you increase the impact energy, it's quite a big increase in impact energy, a factor of 3, the maximum load goes up. In fact, it's an increase of about 80% that you can see over here. And then the other big effect is that the displacement of the panel, when you look at the load displacement trace here, you can see there's an appreciable increase in the displacement as well. So what we then did was to do a C-scan of these panels post impact, and here you can see the 3 panels, 1, 2, 3. Here we have the lower impact energy of 15 joules, and over here on the right we have the higher impact energy of 45 joules. And you can see that this is color coded. In fact, the depth is shown here going from red to blue. So the furthest from the front surface, the impact surface, is blue. The overall thickness of the panel is 3 millimeters. And so this dark blue corresponds effectively to a reflection from the back surface. But you can see there's a delamination just above that. And then as the colors shift to red, those correspond to delaminations nearer the front surface of the panel. Now what is quite noticeable here is that at the 15 joule impact, the extent of the delamination is a lot less. When you go to 45 joules, you get some very big delaminations near the rear surface. Of course, none of this is new, it's all been observed before, but in this case it was quite nice to see that it matched up with what other people have found. Then we went on to look at the effect of impactor shape. And what we did here was to use those 2 different types of impactor. We used the round-nosed striker and the flat-fronted striker. And you can see that in each case we have, on the left here, we have a load time trace. The blue trace here is the round-nosed striker. And then when you go to the flat-fronted striker, flat-face steel striker, you can see you get a steeper rise, the effective stiffness is higher, and it goes to a higher load. It also comes down slightly more dramatically with respect to time. Over here on the right, you can see a load displacement plot, and here you can see again that the effective stiffness is slightly higher, and it goes up to, in this case, you go up to an overall displacement for the flat face steel impactor, which is less than for the round-nosed steel impactor. And over here on the left, we've made a note of the displacements and duration times and so on. So when we're coming on to look at the damage, we observe here on the left we have the round-nosed striker impact, and on the right we have the flat-faced striker impact. And at a glance, again, you can see that the coloured area which corresponds to the delaminations is not dissimilar for these 2 types of impactor. But what is noticeable, and it occurs on all 3 samples, is that for the flat-faced steel impactor, there's a central area here in which there's very little damage. And that's something which we're going to come back to. So these were impacts at the same impact energy for round-nosed and flat-faced steel strikers. What we went on to do next was to model this. Or what I should say, Dr. J.Liu went on to model this, and we assisted in the process, Tony and I and Bamba and Brian as well. And you can see here the round-nosed striker and the flat-fronted steel striker impacting, and it impacts at the center. All of this is modeled. The layup of the composite is modeled, and this shows in quite some detail on the right a flow chart, but over on the left we've given you the essence of what's inside this modeling. It's essentially an elastic plastic or simple flow roll based non-linear model which we use to model the behavior of the matrix. In fact, the matrix we have for this particular study is a toughened epoxy matrix, but this model works very well for carbon fiber peak composites, and that's one of the reasons we've developed. There's the Northwestern University damage criteria, which is built into the model. That's the 3D failure criteria that are incorporated. And there's 2 aspects to this. On the left here we have the interlaminar stream, which you can see, and then on the right we have the intralaminar stream. The intralaminar stream, which relies on material properties and application of the NU criteria, that has a smeared crack approach for the intralaminar damage modelling, whilst the interlaminar aspects of the model, which model the delaminations between the plies, that relies on a cohesive surface model, which is determined by application of this usual relationship, which you can see here. And then after that initiation condition is reached, then you go into the bilinear separation process, which is characteristic of the cohesive surface modelling. So these are the main features. We've got linear softening for damage propagation, we've got a cohesive surface-based interlaminar model, and we've got a smeared crack approach for the intralaminar damage model. So we've applied this now to the impactor shape case, and what is quite apparent here is that you get a very good, what we've done here is to show the experimental data for the 3 round nose striker impacts. This is load time trace, and then we've overlaid on that the simulation which comes from that model that I've just shown you. And you can see here on the left is the round-nosed striker response, and then when you go to the flat-faced steel impactor, again the simulation does very well in representing the higher load and the more rapid rise and fall of load with time. And likewise, when you come to look at the load displacement, that is also simulated very well by the elastic plastic model. In fact, you even pick up some of these dynamic excitations which you see on the rising part of the force, the load displacement and load time traces. Now we come to the delaminations themselves, and you can see here that in the round nose striker impact, you've got, here is the experimental prediction with a color coding giving you the delaminations at different depth through the thickness of the sample. You've got that missing area of delamination which you get in the flat-faced steel impactor, and when you look at the simulation, you can see that the overall shape of the damage area, the damage footprint as we call it, is very similar and representative for both simulations with the experiments. And we also capture this central area where there is very little damage. And the reasons behind this, well, the reasons behind this are that when you look at the Hertzian contact with a round-nosed impactor, you've got a point application of load there, and that gives you this region of high strain gradient from which initially the delaminations will be initiated under mode 1, but then grow under mode 2. But when you have a flat-fronted impactor, you get a much broader area. You haven't got a simple Hertzian contact, and in fact the delaminations tend to initiate from the periphery of the impactor. And this is seen here, this is a side-on view, and you can see here that the delaminations are spread outwards from the center, whilst here the delaminations have tended to congregate around the periphery. This is a blow up of those regions on either side. So in conclusion, the composite specimen struck with a flat-face steel impactor experienced a higher maximum load but smaller outer plane displacement than those struck with a round-nosed steel impactor. Experimental C-scan proved to be very useful in picking up the delaminations, and that was a good feature. And finally, the model that we developed was very effective in modelling both the round-nosed striker and the flat-face striker impact. Thank you very much.